Hello, this video presents an Elsevier book chapter on power quality in modern power systems. The name of the chapter is Power Quality Disturbances Detection and Classification Combining Advanced Signal Processing and Machine Learning Tools. The authors of these chapters are myself, Muhammad Shafiullah, Mir Abdul Mateen Khan, and Shakir Ahmed. We all are from the Center of Research Excellence in Renewable Energy at King Fahd University of Petroleum and Minerals in Saudi Arabia. We can be reached through the provided email addresses. Now let us go quickly over the outlines of this video. At the beginning, we will be discussing power quality disturbances fundamentals, followed by the objectives of this chapter. Then we will briefly introduce signal processing techniques and machine learning models. Then we will be covering feature extraction and machine learning model selection processes. Then we will be presenting the results on power quality disturbances detection and classifications. Finally, we will be putting our concluding remarks on this video. So what are the power quality disturbances? One of the most commonly used buzzwords in the field of power system industry. You can find the definition in IEEE standards, different electrical textbooks, and so on. As you can see in the left side, this is a purely sinusoidal signal, which is expected for all kind of AC electrical appliances. But in reality, this signal is little bit lower than the expected for a specific period of time, or it can be little bit higher, or it can be totally off, or it can be like this one or this one. All of the variations of these signals from the expected signals are known as power quality disturbances. Power system disturbances can occur for many reasons, including the presence of nonlinear loads, the integration of renewable energy resources using power electronic converters, power system faults, lightning strikes, energization of transformers, switching on or off large loads or large capacitor banks. There are many consequences of the power quality disturbances, including malfunction of the protective devices, malfunction of the sensitive electrical appliances, and economic losses. Management of power quality disturbances are very crucial due to the gravity of the topic and the recent addition of power quality disturbances producers. Before 1990s, the researchers used to use manual techniques for the management and monitoring of the power quality events. However, the technological evolution paved the way for better and smart monitoring and management of the power quality disturbances. Researchers employed signal processing based machine learning tools for detection and classification of the power quality events. However, the reported articles rarely compared the performance of the different configurations of the neural networks. This chapter mathematically models 12 different power quality disturbances. Then it extracts the useful features using signal processing techniques. Then this chapter developed the machine learning models for power quality disturbances detection and classification. After development of the signal processing based machine learning techniques, this chapter compares the performance of different configurations of machine learning models. Then it also investigates the robustness of the developed technique under noisy measurement conditions. Finally, this chapter validates the efficacy of the developed signal processing based machine learning techniques for power quality disturbances detection and classification. Now let us have a quick look on the signal processing techniques. The Fourier transform, which is one of the widely used and one of the greatest tools in engineering, which transforms the time domain signal into frequency domain signal. Therefore, it loses time information, as well as it provides erroneous information for non-stationary signals like power quality disturbances. On the other hand, the short time Fourier transform, which provides both frequency and time information. However, it cannot provide better frequency and time resolutions at the same time. Wavelet transform, an advanced signal processing technique that overcomes the shortcomings of short-time Fourier transforms. It can provide better time and frequency resolutions at the same time. However, it does not contain phase information and sometimes it is sensitive to measurement noises. On the other hand, another advanced signal processing technique, which is Stockwell transform, that combines the advantages of both short-time Fourier transform and wavelet transform. Also, it contains the phase information. The short-time Fourier transform uses fixed sampling window, as can be seen from the figures. The top figure is for better time resolution and the down figure is for better frequency resolutions. As they are using fixed sampling window, we cannot have better time and frequency resolutions at the same time. On the other hand, the wavelet transform that uses varying sampling window, it can provide both better time and frequency resolutions simultaneously. These are the mathematical modeling of Fourier, short-time Fourier, wavelet, and Stockwell transforms. Machine learning approaches develop the model that are trained and tested using the known information where both inputs and outputs are known. Then they are employed to provide decisions on the similar events where only the inputs are known but the outputs are not. Artificial neural networks are the widely employed machine learning tools in solving real-life problems due to their abilities of parallel computation and adaptiveness to external disturbances. Other machine learning techniques include support vector machines, extreme learning machines, and so on. In this chapter, we have modeled pure signal as well as sag, soil, fluctuation, interruption, harmonic, harmonic with sag, harmonic with soil, harmonic with interruption, notch, and transient events. In order to get the features from the discrete wavelet transform, the targeted signal needs to be passed through a set of low and high pass filter. The low pass filter will give us approximate coefficient, whereas the high pass filter will give us the detailed coefficient. Then the approximate coefficients will need to pass through another set of low and high pass filter to get another set of approximate and detailed coefficients. And the process continues further until we reach our desired level of decomposition. We have used Debussy 4 as mother wavelet, and we have decomposed our signals into several levels. For example, the harmonic signals have been decomposed into 7 detailed and 1 approximate coefficients. As can be seen, all the coefficients are series of numbers. From this series of numbers, we have taken the skewness, kurtosis, entropy, energy, mean, and standard deviation. Eventually, we will have 48 features from each case. The output of the Stockwell transformation is a matrix whose column pertains to time and rows pertains to frequency. From this Stockwell transformation matrix, we can have the energy matrix. From the Stockwell transformation and the energy matrices, we can have these 4 vectors. From these 4 vectors, we can calculate their standard deviations, maximum values, minimum values, mean values, entropy, skewness, and kurtosis. So, therefore, at the end of the Stockwell transformation process, we will have a total of 28 features. In this chapter, we have used different configurations of feed-forward neural networks. This table provides the specifications of the neural networks we have used for both detection and classification of power quality disturbances. For the development of PQ detection model, we have used 5,000 power quality disturbances samples and 5,000 pure samples. For the classification model development, we have used 1,200 samples of each type. At the beginning, we have used Levenberg Marquardt as our training algorithm, whereas our objective function was to minimize mean squared error. This table provides the objective function values for both PQ detection and classification problems. As can be seen, the ASD-based detection problem achieved minimum objective function while the number of neurons in the hidden layer were 9. Now let us have a look on the detection accuracy of our developed models. As can be seen, the ASD-based approach outperformed the DWT-based approach for both noisy and noise-free measurements. This table provides the classification accuracy of DWT-based approach. It can provide satisfactory accuracy even in the presence of measurement noise. This table provides the classification accuracy of SD-based approach. As can be seen, the SD-based approach again outperformed the DWT-based approach for both noisy and noise-free measurements. To compare the detection accuracies, we have employed different number of neurons in the hidden layers as well as different types of training algorithms to the feed-forward neural networks. Similarly, we have compared the classification accuracies by employing different number of neurons in the hidden layers and different types of training algorithms to the feed-forward neural networks. This is our developed power quality disturbances detection and classification model. For validation purposes, we have applied randomly generated new cases to our developed models. As can be seen, our models have successfully detected and classified all of the applied cases. The summaries of this chapter are: it developed power quality disturbances detection and classification scheme combining advanced signal processing and machine learning tools. It modeled the power quality disturbances mathematically. It employed a discrete wavelet transform and a Stockwell transform for feature extraction. It developed various configurations of feed-forward neural networks. This chapter also validated the effectiveness of the developed models. It was observed that the Levenberg Marquardt training algorithm outperformed other training algorithms, as well as the SD-based approach outperformed the DWT-based approach in most of the cases.